Good morning, students. In this session, we are going to see about the schedulers, how scheduling is important in process management, and also what is process scheduling. Myself, Dr. Shirisha, Associate Professor from CSC Department, MLR Institute of Technology. So, the textbook that we follow is OS Principles, that is Operating System Principles by Galvin. And these are the textbooks that you can prefer for reference. So either you can go for 5th or 7th edition, 7th or 8th edition you can prefer. And Advanced Programming in Unix by William Stevens. So this is also the book that can be referred. And what are schedulers in operating system? We all know whenever the process has to undergo the execution by the processor, there should be a scheduler or a dispatcher which sends the process into the CPU. Therefore, the process will undergo its execution. So, we have different types of schedulers here. So, one is the short-term scheduler, second one is a long-term scheduler, and we also have medium-term scheduler, the third one. Okay, medium-term scheduler. These are the three types we have. So, what is a short-term scheduler is? It is very fast, where it can schedule the process and allocate the CPU. And this short-term scheduler is also known as a CPU scheduler. These are the other name for the short-term scheduler, which selects which process should be executed next. If there are multiple processes, so which process has to undergo its executions towards the CPU. So that can be allocated to the CPU and that can be scheduled by this short-term scheduler. So sometimes only scheduler in a system, and short-term scheduler is invoked frequently every time. It checks how many processes are waiting, and therefore it will allocate the CPU whenever the CPU is free or CPU is idle. So this will be very fast. Whenever the CPU becomes idle, it goes search and allocates the process into the processor. And this coming to the second one is a long-term scheduler. So long-term scheduler is also called as a job scheduler, whereas the short-term scheduler is known as a CPU scheduler. Why this is job scheduler is, which select the process that should brought into the ready queue. You will be having a ready queue where whatever the process that wants to execute, suppose P1 wants to execute, enter the ready queue. If P2 doesn't wants to execute, then it will not into the ready queue. So then if you P3 is ready for its execution, then P3 is allocated into the ready queue. Similarly, P5 if it is ready, P4 then later, then like that this ready queue will be storing all the processes which are ready. Therefore, they can send to the running state. Running state is nothing but allocating the processor to the process. So, it selects which process should be brought into the ready queue. The long-term scheduler is invoked infrequently, maybe very slow. These are fast. Okay, these are little bit slow. But this short-term scheduler, it is very frequent, like how you go and search in the cache memory temporarily and get the data. In the same way, when you have a long-term scheduler, you also search is, the search happens is infrequently. You don't search very frequently, which is happening in the short-term scheduler. And the long-term scheduler controls the degree of multiprogramming. Degree of multiprogramming is a number of processes which are ready for their execution. Number of processes which are into execution. Okay. So, if a processor is idle, CPU is idle, what happens? You have to allocate the next process which is in the ready queue. Like the degree of multiprogramming is, if you have T is equals to 5. If T is equals to 5, if you are giving 5 process for its execution, then the degree of multiprogramming we can say high. If the within time T is equals to 5, if the number of processes that are going to execute is only one, process P1, one process is executing, then your degree of multiprogramming is reduced. That is degree of multiprogramming which is reduced. That means number of processes that you are executing per unit time may vary according to the process functioning and also the processor availability. So based on that, the degree of multi-programming can be handled using this long-term scheduler control. Okay. Then process can be described either two types of process. We have IO-bound process where input-output computations can be happen. So spends more time during IO than the computations. But whereas your CPU-bound process, it spends more time during the computations, not during the IO operation. So this is the difference between your IO process and the CPU-bound process. Okay, bound is nothing but a limit. Okay. Limit, there will be a particular limit of for a process for its execution or for IO to complete. That's a limit that is bounded. Okay, so CPU bound process, which is very concentrating much on the computations, whereas a few very long CPU bursts will be there. Long-term scheduler strives for the good process mix. Process mix means process mix is a combination of both IO and also the computations that may happen. So all this process can be considered when a long-term scheduler is considered. Okay, these are the different types. But what is medium-term scheduler? We know that short-term is very fast and frequently it accesses for a process which are in the queue. Whereas your long-term scheduler is very slow and it is infrequent, may the process become slower. Therefore, the degree of multi-programming can also be considered here in the long-term scheduler. So coming to medium-term scheduler, this can be added if the degree of multi-programming decrease. If you wanted to decrease, you have a processor ideally, but if you don't want multi-programming to happen, means multiple processes if you don't want to execute, then you will call this medium-term scheduler. So it can be added if the degree of multi-programming needs to be decreased. Remove process from the memory. So how you are accessing this medium-term scheduler or reducing the degree of multi-programming is remove the process from the memory, store on the disk. So you have a memory, okay, and you have disk. So from the main memory, you are storing that into the disk and bring back from disk to your main memory. So this is main memory, maybe this is a disk. So when you are sending, okay, this is, we can call it as out operation and this is in operation. Okay, swap in, swap out, we can call swap out and swap in. So when this process is occurring, then your disk is scheduling the process into the main memory. Main memory is sending the process into the disk whenever there is no availability of storage into the memory. So this process we are calling it as what? Swapping. This is swapping. Okay, so here we have, you have a CPU, a processor, and you have a ready queue. And when you wanted to execute a process, the input is given into the ready queue. From the ready queue, the CPU will be allocated. And once the CPU is allocated, you can execute the process. And whereas your CPU, if there is no memory here, then one process, say one particular process PI, should be swapped out. Therefore, this particular process can swap in. PJ can swap in. PI will be out. Okay, in that way, what we are doing this swapping process. We are calling it as a swapping. If there is a computational, this is a IO operations, or these are process computations. So any type of process, there's a bound there. So whenever there's a limit, for that particular time only your process can execute. Later on it will come back if it is going to the waiting state. Therefore the swapping can be done. Meanwhile the other process can execute its process. In this way, the scheduler, whether the medium or short or long, the scheduler has to check in a way that the process has to allocate the CPU always. The CPU should not be idle anytime. So in that way, the degree of multi-programming is increased and is controlled. Okay. And coming to context switches, whenever you are shifting, that means suppose if you have here, you are swapping out and you are swapping in. So what is happening? It is switching from, you have a process P0, P1 and P2. Your context switching, this is going into the IO operation. Therefore, this is swaps with some other process, say P3. So what is that? There's a context from here to here, from here to here. It is switching from one process to other process. Whenever the process of switching from one process to other process to allocate the CPU for its execution, then we can call this as a context switching. So when CPU switches another process, the system must save the state, whatever be the state, like you have new, ready, running, terminate, waiting, interrupt. So such states you can store it. You have to save the state of the old process and load the saved state for the new process via the context switch. This is just like whenever you have a main memory, whenever you have a disk, then whenever you are doing such out operation and in operation, then what is happening here? You are sending one process pi to from main memory to disk. Now this process pi space is empty. Now this, when the swap in operation is done, in here this may be replaced with pj. So this is called what? Context switching. There is a switch from one process to other process. Context of a process represented in the PCB. There is a process control block. Context switch time is overhead. Okay, the system does no useful work while switching. It's an overhead, means whenever it is switching from one process to other process, it takes time. So if that particular time is an overhead for a context switch, it's a context switch time is overhead. The system does no work. It is not doing any work. It is just swapping the process, one process to the other. So more complex the OS, the PCB, the longer the context switches. So more complex the OS means whenever it is taking much, like a round robin. If you take round robin process scheduling, what happens? You have a process and that process has to execute only for a particular time period, the time quantum or the time slice. Later on it has to again swap with the other process. Again that will undergo the, you have a process. So P1, if the P1 burst time will be, say it has 20 and you have a time quantum which is of 10. So this P1, even though its burst time is 20, how much time it will execute? It will execute only for 10. So 10 milliseconds. Then afterward, if you have a P2, say P2 is having 5. So as the time quantum is higher than the given process burst time, therefore it will execute for the 5 milliseconds. But after P2, again the P1 has to execute. The 20 out of 20, only 10 has executed. So the remaining 10 has to be executed again for P1. So there's a switch for the P1. Here it is executing. Again it is context switching to P2. Again it is switching back to P1. So like that, what if you have multiple process, 1 to 100, say thousands of process, then what happens? The context switches will be higher. So time dependent on hardware support. Yes, you need a hardware support where it gives address of a particular location so that your process can be stored. Every time whenever your PCB is switching, there's a context switch, the PCB has to store its state. So some hardware provides multiple sets of registers per CPU. The multiple contexts loaded at once. So if there are multiple switches, means multiple contexts can be loaded. This is about the context switching, and we see what are the operations or the processes will undergo. Okay, so system must provide a mechanism, one for process creation and the second for process termination. Okay, so what is process creation and what is process termination? We'll see. Parent process create a children process as a child process, or how to create a child process which in turn create other process forming a tree. If you have, say, P1, it is creating two processes, say P2, P3. Again, P2, P3, they are creating P4, P5, and P3 is creating P6, P7, let us say. So, what is happening? This is a parent process. This becomes a parent process, whereas this becomes the child process. This also one child process 1, child process 2. So, like that, there may be a tree formation whenever there are multiple child processes that have been created. So process identified and managed via process identified. We all know that every process will have a process ID, PID. Resource sharing options. So whenever you have a parent process and the child process, how a resource is shared, a resource sharing is happened is parent and children share all the resources. Yes, whatever the resources that are there, that is shared by all the process, either it is a parent or either it is a children. Children share subsets of parent resources, obviously, like a hierarchical structure, and parent and child share no resources. This also may happen sometimes. They will not share the resources. So these are the resource sharing options that we have. Either both can share or either both cannot share them. Then execution options. Parent and children execute concurrently, one after the other, or they can simultaneously can use. But sometimes parent has to wait until the child process is terminated. Parent cannot execute parallelly whenever your child process or child process is getting executed. So it has to wait until the parent child process is terminated. And this is the tree structure, whatever we have seen. So as I told you, P1, P2, this is P1, P2, P3, say P4, and P5, P6, P7, P8, P9. So like this, there are some process. So this can form a child tree structure. This is a tree structure, and these all can become a child process. So how to create this child process is again a query. So based on the operating system, it varies. So this is a init process where this can be a parent process. Init is always a parent process. Okay. And this is the PID. Every process is having a PID, whereas if you see, everything is unique. PIDs are always unique. You don't have the same ID for two different processes. If you see here in this diagram also, you have a unique numbering that is given, different IDs that are given for each process. Okay, this is like in Linux, this happens like login, kthread, and that is a shell directory, bash process, helper process. So like this, these are the different processes that we have with respect to Linux operating system. How do you create a process? So process creation is again one important thing that you have to know. And fork is a system call that is always used for creating a new process. And you need address space. A child duplicate of a parent, that is address space. Child has a program loaded into it, that is also fine separately. And Unix uses a fork system call for creation of new process. Is a fork system call for creation of a new process. And you have execute system call, which is used after the fork to replace the process memory space with a new program. So execute the process. So the parent fork is creating the child process which undergoes execution and it exits. Until and unless this is executing, the parent process is waiting. So once this is executed, the parent process again resumes and it will exit. So this also happens sometimes. So whenever the child process is executing, parent process has to wait until the child process is executing its job. So this is about the fork system call that we have discussed system calls in the first unit. So this is one of the example for the system call. And you have a program where you're creating a child process. So here if you see, we have a C program example. We have types, different types of system calls which can be liked in this header file. And stdio input output header file, uni std system, uni std header file, and all these header files will support the system calls and the statements that we are writing in this program. So PIDT is nothing but you are writing a process, and this is PID. PID is nothing but it's a process to create a process ID. Okay, and fork a child process. So you are calling this PID. PID is assigned with the fork. What is fork? Fork is used to create a child process. Create a child process. So whenever the child process is created, it will get a new ID that you are going to store into the PID. If it is really created, then if you have to execute it, just you are executing the child process just by simply giving EC, that is execution of LP list of processes, that is ls command. Okay, if PID equal to 0, if it is less than 0 means an error. So it will give you a standard error, fork failed. That means your child process has not created. Okay, here child process creation fails. It fails creating the process. It is successful creation. Upon successful creation, you can just list the process. Else, parent process will wait for the child process to complete. There's a wait system call is used. Then child complete. If the child is completed, again the parent process can run its execution. This is a simple program that you can give as an example of how your child process are getting created. And process terminations. Once the process is created, you have to terminate the process. Process executes the last statement and then asks the OS to delete it using the exit system call. So once fork is created and if you wanted to exit, then you have to use this exit system call. Returns the status data from child to parent, so via wait system call. Process resources are also deallocated by the operating system. When you want to execute a process, then it is allocated. When your execution is done, if you have executed and process has been completed its job, then what you have to do, you have to deallocate it, okay, by the operating system. Then parent may terminate the execution of the child process using abort. What happens? You have a parent process, you have a child process. If you are sending an abort the system call, child process has to stop its execution. In that way, the execution of the child process is getting terminated. The child has exceeded some reasons why we have to stop the child processes. It has exceeded the allocated resources. If you are executing multiple times that child process is getting executed, then you have to terminate that can be done using this wait system call. And task assigned to this child is no longer required. If you want only the parent process to get executed and child process need not get executed, then you have to terminate it. That is where one of the criteria where you can terminate it. And parent is exiting and the operating system does not allow a child to continue if it is parent terminates. So parent is exiting and the operating system does not allow child to continue if it is parent system. It means parent and child process both parallelly, concurrently they have to get executed. If parent is waiting until and unless the child is terminated, that is also one case. The other case is where you need a parent process also to execute parallelly with the child process. And how the process terminated. Some operating systems do not allow child to exit if the parent has terminated. So both cannot terminate. If process terminates, then all children must also be terminated. These are also two cases. When your parent is exited, then all your child process, means the threads that are under the parent also can be terminated. So this is all children are terminated means we call it as a cascading termination. If you have one parent and if you have multiple child process, child 1, child 2 and child 3, okay, and you have child 4. So when you have multiple process like this, if this is terminated, exit system call, then all this automatically exits. This is one of the criteria. This is called as a cascading termination. Okay. And this termination is initiated by the OS, and the parent process may wait for the termination of child process by using the wait system call, of course, and call returns the state information and PID of the terminated process. So what is this? It returns the status of the wait system call using the wait system call, and it returns to the PID. Therefore, the process can be terminated. If no parent is waiting, then the process is called as a zombie process. Did not invoke any wait system call. If no process is waiting, then you call it as a zombie process. If parent terminated without invoking waiting, process is a orphan. Okay. If no parent waiting, then it's a zombie process. If a parent terminated without invoking the wait, means you are not it has not waited but it has been terminated, then it will become a orphan process. So zombie and orphan process, two important differences you need to know. Okay. These are the topics that we have discussed so far. How to schedule a process, what are the different ways of scheduling, long term, short term and medium term schedulers, and how a process can be created, how a process can be terminated. Hope you all understood. Thank you all.